Computational synergy, bridging quantum mechanics and chemical engineering through numerical parade solutions. Introduction. At the heart of understanding and manipulating the physical world lie partial differential equations, PDEs. These mathematical constructs describe phenomena ranging from the probabilistic behavior of subatomic particles to the transport and transformation of chemical species in reactors. While the physical domains of quantum mechanics, QM, and chemical engineering might seem disparate at first glance, our computational exploration has compellingly demonstrated a profound connection. Numerical methods for solving PDEs serve as a powerful, common language, creating a bridge between these seemingly separate scientific realms. Through a progressive series of Python scripts, particle_in_box.py, numerical_to z_solver.py, and reaction_diffusion_solver.py, this project successfully implemented numerical techniques while maintaining crucial ties to underlying analytical principles, showcasing a versatile template for tackling complex problems in both fields. Quantum foundations, from analytical exactitude to numerical necessity. The initial step in this computational journey, particle_in_box.py, grounded the exploration in a cornerstone of introductory quantum mechanics, the infinite potential well. This idealized system, solvable analytically, provides fundamental insights into the consequences of spatial confinement for a quantum particle. The script's output of psi_n, the wave functions or eigenfunctions, and e_n, the corresponding energy levels or eigenvalues, directly visualized core QM principles, the spatial quantization of wave functions, meaning the particle's probability distribution exists only in discrete, specific patterns within the box, and energy level discretization, where the particle is restricted to having only specific energy values proportional to the square of an integer, proportionality n squared. The probability density distributions, x squared, clearly showed where the particle was most likely to be found for each energy state. This initial script, leveraging known analytical solutions to the time-independent Schrödinger equation, =E, served as a vital benchmark, providing clear, predictable results against which subsequent numerical methods could be conceptually compared and validated. Building upon this foundation, the numerical_to z_solver.py script ventured into more complex territory by tackling the harmonic oscillator, a system ubiquitous in physics and chemistry, representing molecular vibrations, for example. While the harmonic oscillator also possesses analytical solutions, E=n+1/2, this script shifted the focus to a purely numerical approach for solving the time-independent Schrödinger equation. The core technique involved discretizing the Hamiltonian operator, h, using the finite difference method, approximating the second spatial derivative, nabla squared or del squared del x squared, as 2 plus x squared. This transformation converted the continuous differential equation problem into a discrete matrix eigenvalue problem, effectively x equals x, or in this case, a matrix representation of h acting on a vector representation of psi equals E times the vector representation of psi. The power of the scientific Python stack was harnessed, specifically scipy.linalg.eigh, to efficiently solve this matrix equation and obtain the numerical eigenvalues, energy levels, and eigenvectors, wave functions. Comparing these numerical results to the known analytical solutions for the harmonic oscillator served as a critical validation of the numerical method's accuracy. Furthermore, the script provided visualization of a uniquely quantum phenomenon, probability tunneling. Unlike classical particles, the quantum harmonic oscillator's wave function does not abruptly drop to zero at the classical turning points but extends into classically forbidden regions, indicating a non-zero probability of finding the particle there, a concept that foreshadows the tunneling explored in the initial summary's third script. Chemical engineering translation, from reactivity to reactors. The project then demonstrated the remarkable versatility of these numerical techniques by translating them to a seemingly different domain, chemical engineering, specifically the analysis of a reaction-diffusion system. The reaction_diffusion_solver.py script adapted the numerical framework developed for the time-independent Schrödinger equation to solve a different type of parade, a boundary value problem describing the steady-state concentration profile within, for example, a porous catalyst pellet undergoing a first-order reaction. The governing equation, d nabla squared c, Kc equals 0, describes the balance between diffusion, d nabla squared c, and reaction rate, Kc. Crucially, the numerical approach mirrored the quantum solver. Spatial discretization using finite differences transformed the continuous parade into a system of linear algebraic equations, which could again be represented in a matrix form, analogous to Ax equals B. The Python code snippet provided, detailing the construction of the core matrix M with terms alpha equals d underscore f, dx squared and beta equals -2 asterisk alpha, k underscore 8, clearly shows the finite difference approximation of the second derivative coupled with the reaction term, mirroring the structure seen in the discretized Hamiltonian matrix. Key achievements in this chemical engineering application included the successful implementation of Newman boundary conditions, dc, dx equals 0 at the center of the pellet, representing symmetry or no flux, a crucial departure from the Dirichlet boundary conditions, psi equals 0 at boundaries, common in simple QM box problems, demonstrating the adaptability of the numerical framework. The script also enabled the calculation of the effectiveness factor, eta, a vital performance metric in catalytic reactor design determined via numerical integration of the concentration profile. Sensitivity analysis regarding the Thiele modulus, phi, dimensionless number characteristic of reaction diffusion systems, analogous in its role to the quantum number, n, in characterizing system behavior under competing effects, allowed for exploration of how kinetic and diffusion rates influence reactor performance. Validation against the analytical solution eta equals tan, phi for this specific system confirmed the numerical method's accuracy in the chemical engineering context. Computational methodology unification and profound parallels. The success of this project hinges on the underlying computational methodology unification shared across both domains. Despite the vastly different physical interpretations, both the time-independent Schrödinger equation and the steady-state reaction diffusion equation, under the chosen conditions, reduced to forms solvable by similar numerical techniques. The core shared methodologies include spatial discretization. Both problems were solved by dividing the continuous spatial domain, position x, into discrete points with a defined step size x, allowing the PDEs to be approximated algebraically. Second derivative approximation. The crucial link was the finite difference approximation of the second spatial derivative, applied identically in both the Hamiltonian operator and the diffusion term, del squared, del x squared almost equal to 2 plus x squared or c, 2c plus c, x squared. Matrix equation construction. This approximation transforms the differential equations into systems of linear algebraic equations that can be represented and solved efficiently in matrix form. The structure of the resulting matrices captures the interactions between adjacent spatial points, representing either quantum mechanical coupling, Hamiltonian, or mass transfer and reaction, diffusion reaction operator. Scientific Python stack. The reliance on libraries like NumPy for numerical arrays and operations, scipy for linear algebra solvers, and matplotlib for visualization, underscores the common toolset available for tackling problems across scientific disciplines. The explicit parallels drawn in the summary table highlight this deep mathematical and computational connection. Both systems are governed by PDEs that, after discretization, lead to matrix problems. While the physical interpretation of the key matrix, Hamiltonian versus diffusion reaction operator, and the boundary conditions, Dirichlet for the infinite box versus Newman for the catalyst pellet, differ based on the specific physics, chemistry, the underlying computational task involves constructing and solving a matrix equation derived from spatial discretization. Furthermore, both fields utilize dimensionless numbers, quantum number, n, and Thiele modulus, phi, to encapsulate the interplay of fundamental effects, confinement, energy versus reaction, diffusion, and characterize system behavior. Conclusion. In conclusion, this computational journey compellingly demonstrates that numerical methods for solving partial differential equations serve as a powerful, unifying bridge between the fundamental principles of quantum mechanics and the applied challenges of chemical engineering. By adapting finite difference methods and matrix solving techniques initially applied to the time-independent Schrödinger equation, for the particle in a box and harmonic oscillator, to a reaction diffusion system, this project established a versatile template for analyzing diverse physical phenomena. The modular structure of the developed scripts allowing for easy substitution of quantum potentials or chemical kinetics highlights the adaptability of this computational framework. This approach provides a robust foundation not only for understanding the specific systems explored but also for future investigations into more complex scenarios, including nonlinear systems, time-dependent phenomena, and multidimensional extensions in both the quantum and chemical engineering realms. The synergy revealed through these computational explorations underscores the profound interconnectedness of scientific disciplines through the universal language of mathematics and computation.